Hello, hello, test. Okay, good, good. Okay, we'll get started. Hello, everybody. Thank you for coming to the second undergrad colloquium. Today we have Vivek presenting quantum computing hardware and today's quantum ecosystem. So we'll give him a big round of applause.
Awesome. Yeah, thank you, Marty, and thank you, PhySU, for organizing these colloquiums. It's very nice to be here and present today. It says today's ecosystem, but I realized that maybe in comparison to how much I'm going to be talking about hardware, it'll be just a very small fraction, but still I hope to deliver almost all the players that are in the game today on the screen and then talk about a couple of them. But anyways, today's talk, I'll start with sort of introducing this weird technology called quantum computing, why people are interested, why you should care, what sort of applications are there in real life. I know, physicists love to look at things just for curiosity purposes, but engineers, as I am really into how can these devices actually be fabricated and optimized for the applications they're being meant to be used for. So specifically, two of them I'll dive into: semiconducting spin qubits, which are made via a semiconductor substrate, and also superconducting transmons, which is made via superconducting material. So two of these topics, simulation and production CMOS technology and 3D integrated flip chip, are topics I worked on through 2 summers of research. Don't worry, it's a lot of fancy words, but I will get into what each of those mean when the slide comes. And then finally, I will be shamelessly plugging QSite Toronto 2024, which is definitely something you guys should be attending. Oh, definitely, yeah. Cool, is that good? Yeah. Awesome. So why is quantum cool, right? Why are we looking into this as a potential way of doing computing, as the name suggests, quantum computing? Well, there's 3 physics-related reasons why it makes sense to look into quantum computing as something that could be better than what we have currently in our phones, laptops, TVs, etc. First is this principle called superposition, right? So if you go to these nanoscopic, microscopic scales, things can be 2 things at the same time. And when I say thing, I'm describing a state. Right? You see something that has 5 volts on it. You see a wire that has 0 volts on it. That's a measurement. That's a thing for today's purposes. So I can assign 5 volts on my capacitor as a classical 1 and 0 volts on my capacitor as a classical 0. But can I make something, some qubit, something that can have both these properties at the same time? Right? And classically, it's very hard to think of an example because you require quantum physics to get to this level. And this is something that's called a qubit, and it uses the superposition principle. Along with it, you can also do something called entanglement in quantum physics, which is essentially relating two of these entities called qubits in such a way that you know the behavior or the state of one given the state of the other. And this is also something that's hard and difficult to do in classical physics. Finally, interference. If you've taken a quantum mechanics course, you would have come across the double slit experiment, but essentially the point of this phenomenon is that there's, at the quantum level, we can't describe things as particles or waves. You have to look at sort of the intersection of them, and what that creates also helps these algorithmic people in the field to develop these super cool algorithms. What are these algorithms useful for, right? Before we get into that, I want to make a distinguishment between bits and qubits. In classical computing, bits could be represented via zeros and ones, but in quantum computing, bits inherently have to be represented in this sort of superposition state of 0 and 1, right? And physically, it could be, suppose the spin of an electron. In chemistry class, you might have learned, okay, spin is down, spin is up. But there are certain states I could create my system in where the spin is both up and down at the same time, or 50-50 probability distribution, and we can get into that as well. In superconducting circuits, it could be magnetic flux through a device. If it's this value, it's in one state. If it's a certain other value, it's in the zero state. And you don't know which value it is in until you measure. And that is also a probability distribution useful to make a qubit. What are some applications? Primarily at this stage, people are looking into drug discovery, material science, cybersecurity, quantum machine learning is popping off. Optimizing logistics using these devices is also popular, and all the business people are looking into optimizing their portfolios using some sort of quantum advantage. And whenever you hear sort of the most biggest hype word, I would say, is this quantum secure communication networks. You know, I don't want an eavesdropper to listen in on my conversations with someone, and hence I'm going to protect my communication network using quantum, right? I sort of heard about this today, so I added this point in. It's like creating Wi-Fi on Mars, right? Eventually we'll go to Mars, and eventually we'll need Wi-Fi, but it's good to start thinking about it right now, right? Eventually we'll have quantum computers strong enough to eavesdrop on your DMs with your friend. Hence, you should start worrying about that right now, right? And that is where a lot of money is being thrown currently in industry. But anyways, today I want to focus on the hardware for the most part. There's a bunch of ways of how you can create these hardware systems. There's semiconductor spin qubits and superconductors that I'll go over. But there's also photonics using light that Xanadu does, a company here in Toronto. There's also Majorana qubits, which is still in its beginning phases, but it's sort of a topological way of doing quantum computing. We have trapped ions, which IonQ is a leader in, and is sort of the most oldest hardware platform, I would say. And there's also spintronics and nitrogen vacancies, and there's way more, or not way more, a few more that I didn't put on the screen. But like I said, we'll focus on the first two for today. To get into semiconducting quantum computing, let me first get into semiconducting classical computing. Here is a picture of a a transistor. So there's a billion of these in our everyday electronics, phones, TVs, etc. We have this substrate of silicon, let's say, and we have these red regions where we dope a lot of electrons. So we forcefully sputter a bunch of electrons, which now get deposited in this area. So now we have excess charge. We also put some metal in yellow in these certain places, and then in the middle, we separate the metal with the semiconductor using an oxide. And now you're saying, like, why are you telling me this? Why? Like, every single sentence I said, you could ask me, why are you doing this, right? But just trust me on this, and now if I do certain voltage variations, interesting things will happen. So now I want to increase the voltage on this metal gate, okay? That will attract electrons. Since it's a positive voltage, negatively charged particles, electrons will be attracted to this metal. But because we put that oxide, it won't exit this device through the metal. So they would sort of start hovering in this area called the channel. If I increase this voltage significantly enough, this is called the going beyond the threshold region, I create an inversion layer in the substrate, and now there's a constant presence of electrons. And now the purpose of the other two metals is clear. If I add some voltage to this node, which we call the drain, electrons will start flowing towards it, right? And now we have current going in this direction, since electrons are going in this direction. Great, we have current, we have a transistor, but how can we connect this to quantum computing? Well, earlier I said that one of the mechanisms we can store this thing called qubit is in the spin of an electron. Well, I see a bunch of electrons here. How can I, take one, tell it to be where it is, and now play around with its spin for quantum computing? I can make these devices extremely, extremely small. and put them at extremely, extremely cold temperatures. If I do that, this is something that can be achieved. This is sort of a potential diagram of the transistor from earlier on. Here's your source, here's your drain, and here's your middle metal region. Because we've made it so small, if you have not taken a quantum mechanics course, let me tell you that when the confinement of an electron gets to a certain degree, you get discrete energy levels forming in this well. So this is, you can think of this as a quantum well, and you have now discrete energy levels forming. Now let me explain other parts of this diagram. We have this sort of blue ocean-like thing on both sides. That is the Fermi-Dirac distribution. And essentially what that means is that this vertical axis is energy. The higher you are in this diagram, the more energy you have. And this axis pointing to the left is probability. What is the probability of me finding an electron of this energy? Well, it's 100%. Because the temperature is 0, this is sort of what this graph looks like, where low energy states are all filled, and at a certain point, called the Fermi level, you have this sort of steep reduction in probability. Same with the drain side, and you'll see why this is useful in a bit. I won't go over the requirements. If we have time, maybe I could answer those questions later, but just for the purpose of time, I'll skip over them. Here's for finite temperature, right? What if I increase the temperature a little bit? I'm not increasing it too much. I still want to, isolate these electrons and not make them fly off because of how hot, room temperature is. So let's say 2 Kelvin is what our temperature is. In this case, you can see these Fermi-Dirac distributions smoothing out, and that creates tunneling possibilities. Right? In quantum mechanics, because your electrons, your particles have this thing called a wave function, which is a spatial probability distribution of finding this particle, there is a very small probability the particle, the electron, will just tunnel from the source into the gate. Right? These vertical sort of pillars are regions where the electron does not want to be. And another slide later on will sort of give you an intuitive feel for why that is. So let's say this is our configuration of energy states. You see that there's this high probability an electron tunnels from the source into this energy level, and then again tunnels out into the drain. So now we have single electron transport. Right? This is how you can get a single electron to occupy your transistor at for a certain given amount of time. If I increase this gate voltage like I did earlier, these energy levels can come down, and you can get a situation like this. Now notice how the Fermi energy levels at the 2 source and drains do not encompass an energy level for the electron. This makes it such that an electron will tunnel into this lower energy state, but will not be able to tunnel out, right? And this energy state, you may say, okay, well, one might tunnel in here and then move out. Well, the probability of an electron being able to tunnel is quite low. So in this situation, you won't have transport through your device. So what have we seen? We have seen a peak in conductance, and in the same device, we have seen a valley in conductance, right? And we can plot this. We have 2 variables in our control, the gate voltage and the drain voltage. Just to get used to the terminology, here's your gate voltage and here's your drain voltage. And you can see that these darker regions correspond to low current, and these lighter colorful regions correspond to high current. So if you take a sort of a horizontal cross-section of this current voltage characteristic, you'll see these peak, valley, peak, valley, peak, valley. And the interesting thing is that there's single electrons causing these currents, and not a bulk movement of electrons that you see in everyday resistors and devices. So this is cool. How can we make, again, quantum computing out of it? I still haven't gone to the point of, qubit 0, qubit 1, superposition, blah, blah, blah. Well, you have to apply a DC magnetic field to the system. And once you apply this DC magnetic field, you might remember from chemistry class that the Zeeman effect is turned on. And if you're first years, don't worry, you'll learn about this soon. I can give you a short summary. It essentially says that by default, without a magnetic field, your electrons can be spin down or spin up. Both of these energies are degenerate. They're the same without magnetic field. But once you apply magnetic field, in this case, I've shown that the spin down state and the spin up state change in energy values. And once you solve the Schrodinger equation, you can see that splitting in the eigenenergies as well. But now I can assign the spin down to be the 0 state, and I can assign the spin up to be the 1 state, right? And this is how I can do quantum computing. How do I transition between these two, right? How do I do the computing part? Now I got the quantum part. You see, this is only possible because of quantum. How can I do the computing part? Well, I don't want to go through all the math because it's literally 2 pages of Wikipedia math that you have to do to prove it, but you can apply an AC magnetic field to your system in a direction perpendicular to your DC magnetic field, right? And once you do that, you get these coherent transitions between the spin down state and the spin up state. And this is something that this plot shows. Don't worry if you don't understand it fully, but essentially for a given external magnetic field, which is our DC magnetic field, we see these oscillations in the current, which is an extrapolation of the state the qubit is in. Yep, so here's some real-life examples of what they look like. So far, I've just shown you sort of pictures and diagrams. Again, this is a picture diagram, but this is way more realistic. It's a cross-section of this device. Here you have your source and drains, and look at this, the scale here. It's 100 nanometers. So these are super, super tiny devices. And in the pictures I gave you, you had 1 quantum dot, you had 2 quantum dots. But here you have 4 quantum dots able to do multiple qubit operations at the same time. So this is a one by Leti in France. This is another image from Intel. Intel is also in spin qubits currently, and you can see that they have sort of 7 gates back to back to back between their source and drain regions. Again, the scale is 100 nanometers, super, super tiny. So now I want to get into some of the research work I have been involved in over the past 2.5 years. This is the first project I got into. It was involving simulation of these transistors and seeing if we can optimize the design via these atomistic simulations. So a little spiel about simulations. Everyone in electrical and computer engineering does simulations of their circuits, of their devices, etc. But most of the simulators that they use think of electrons as this gas, as this bulk ocean of particles with negative charge, right? But you cannot think of that when you're doing quantum computing, because the inherent property that these electrons have a wave function is going to be useful in saying, okay, in dictating whether this device is, optimized for our purposes. So this simulator is called Quantum ATK. It's provided by Synopsys. It treats electrons as wave functions. It solves the Schrodinger's equation in the back end. But essentially, I'll show you plots that don't get into that nitty-gritty detail. I believe the last PhySU Colloquium talk was on DFT, density functional theory, which is the backbone of how these simulations were actually done. So again, hopefully there's some similarities that you can notice. Here's our source. Here's our drain. They're both doped with extra electrons. Here's our channel. And notice I have 2 gates now, 2 metals. And sorry if I say gates and metals interchangeably. It's a sort of a physics versus ECE notation, or way of labeling things, they essentially mean the same thing. So this metal will control sort of the electrostatic environment in the middle region, which is where our qubit will be housed. And this back gate will control the electrostatic region of the entire device. And once I get to double quantum dots, this is a single quantum dot. Once I get to double quantum dots, it might make more sense why this bottom gate is needed. So for research purposes, we wanted to make this device as similar to realistic devices as possible. This work was done with Soren Wojniewski's group in U of T ECE. We send our designs to global foundries to be fabricated, and obviously it's very difficult to tap into what this device actually looks like, but we can emulate it as best as possible. And one of the features of this device is that there's an oxide layer separating the gates from the channel. There's an oxide, this purple indicates an oxide, and that it separates the silicon atoms that you see here from the metal gate. And that oxide is 20 times thicker on the bottom side than the top side. And that's why we changed the permittivity for the quantum dot region, and everywhere else it was 25 under the top gate and 4 everywhere else to sort of emulate that. Here's the double quantum dot. It's sort of the same structure, but instead of the back gate encompassing everything, it's only encompassing the region between the 2 top gates. And now you can maybe get an intuition for why that might be needed. Say we have an electron here, and we have an electron here. We have an electron under the top gate 1 and an electron under the top gate 2. I want to isolate them. I want to not have them interact with each other. I just want them to stay in the state they are. Right? In that case, I want a big potential barrier in the middle. Right? And I can create that using a very, very negative back gate value, metal voltage value. Suppose I want to interact them. Suppose I want to do a 2-qubit operation. I want to, depending on the state of one of the qubits, I want to do this certain operation on the other qubit. In that case, I can lower this barrier and do some fancy stuff with microwave pulses and AC magnetic fields, blah, 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 to make that happen. Right? So that is the sort of purpose of your back gate. Any questions on this work so far? Because that, oh, sorry, there's a question? Oh, good, okay. Because that prepares us for some sanity plots to answer the question, are these devices really working or not, right? Because I can create any device and show you pictures of it, and you'll be like, okay, yeah, that works. But until I give you actual measurements, you're not going to be fully convinced. So here's another current versus voltage plot. I'm varying the voltage of the top gate on the x-axis, and then measuring the current through our devices. And you see, if you focus on one of these plots, say this blue one on the right, you see this peak in conductance, and then a valley, and then the peak in conductance in the valley, and so on and so forth. Right? And this first peak corresponds to 1 electron in your transistor. The second peak relates to the second electron tunneling into your transistor, and so on and so forth. And as I change the back gate that encompasses the entire device, I can actually move this transfer characteristic, it's called current voltage characteristic, to the top left. Right? As I increase the back gate voltage, I'm making it more easy for electrons to come in and out of the device, increasing the current. So this plot on the right might be more intuitive for that purpose. I'm plotting the potential profile of the device, which basically means x-axis is the length of the device, source on the left, drain on the right, and the potential is dictated by your the voltages that you apply to the gates and your ungated regions. So by what I mean by ungated regions is that if you see here, these 2 regions have a very low exposure to a metal gate. And that's why electrons don't like to be there. Electrons want to go towards potential, which is applied on the metal gates. And hence you see these spacer barriers is what they're called, regions where you have this high potential. And if you look closely, you can see that this is indeed a quantum well, right? You have these big, this is a finite quantum well. It's not an infinite quantum well, a finite quantum well with these regions corresponding to your plethora of electrons, you could say, source and drain doped regions. And then as I vary the back gate, which expands the entire device, I can reduce these barriers as I please, right? And the more sort of flexibility I have with my device, the more control I have over my device. Oh, I want to change this. Well, change the gate voltage. I want to change these barriers. Change the back gate voltage. I want to connect this quantum dot with the other quantum dot. Change the back gate region. The more control I have over these devices, the easier it will be to do quantum computing, right? From an engineer's perspective. So here's another research problem that was attempted and is currently being solved through this tool, quantum ATK. Can we optimize the double quantum dot design based on these things called parasitic barriers that form? So I'll have a plot in the next slide that shows you what that means, but I have multiple ways of creating this back gate, this barrier gate. You see, in each of these structures, the top gates are the same, but the way I design the back gate is different, right? Here it's actually a top gate. Here it's a small back gate. Here it's a bigger back gate, and so on. So let me explain sort of why each one of them is under consideration. This is currently what we have in industry. This is what's able to be fabricated now. This design, design B, is something that has potential to be sort of the best solution because it has the greatest control over the middle barrier region. C is something that's that could be done, but might not be the best, so we wanted to test it out anyways. And D is again one of the good solutions that we would like to have because it covers just enough of the area to control the barrier region. However, it's very hard to fabricate D given certain restrictions that these foundries produce. So here are the potential profiles of each of these devices. And again, you see that with the extended back gate, as you change the back gate voltage, which is going from blue to red, I'm changing the back gate voltage. Not only do I get to reduce this middle barrier, but I also get to reduce these quantum dot barriers, right? And that might not be ideal because now you're basically changing the energy value of your qubits. In the space top gate, you actually see these sort of parasitic barriers forming, right? You see this another quantum dot forming in the middle, which is again non-ideal, right? If you're expecting there to be two quantum dots, why would you want to accidentally create a third one? Same with this selective spaced backgate, and then the selective backgate, the last design on the previous plot, you can see that it's sort of the most ideal where you're not hindering your quantum dots, which are here and here, but you're also controlling your barrier. So this was just some design design insights that we got through these simulations, and there's more work to relate these to experiments and etc. Before they could be actually useful to the field. Great. Yeah, this is I explained one of these. Here's another project that I was involved in over this summer actually, and it is about 3D integration of superconducting resonators for fast readout of germanium quantum dots using flip chip technology. So let me explain each one of those words. Usually what happens is that you have one chip, it has the qubits, it has the other electronics that you need, it has the readout mechanisms to measure your qubit, et cetera, all on one chip. Which means physically, if you think about it, you have to fabricate this chip together in the clean room or in your fabrication facility. So while you're working on the electronics, you have to be mindful of the qubits that are still there, right? And vice versa. And that really poses limitations on how creative you can be, or how resilient you can be, or how good your yield is for your devices. So why not split these two functionalities, put the qubits on one chip and put the other electronics on another chip, right? So you're keeping the sensitive qubits away from the electronics during fabrication. So that's what I've sort of depicted here. We're going to use fab pros A for qubits, and then fab pros B for the other electronics. And then finally, we're going to put one of them on top of the other using these super neat engineered bumps called indium bumps, which is essentially, well, you have your substrate on one side, and you put some titanium, platinum, gold. This is one of the examples from literature. They have certain properties like adhesion and diffusion and conductivity, which you might be interested in. And hence we have that sort of underbump metallization. And then finally, you have this 3 to 8 micron tall indium column acting as the glue between these two chips. So I hope that clarifies the 3D integration part of it. We're creating processors that are extending in the third dimension. We're using superconducting resonators to do the measurements of our devices, and I have a design on the next slide that will show you that. And we're doing this on germanium quantum dots, which means this green chip will have your superconducting resonators, and your purple qubit chip will have your germanium quantum dots. And then this process is called flip chip. Here's sort of the fabrication flow. I was also involved in the fabrication this summer, so actually going into the clean room and making these devices with the equipment that they have there. So we started, first on a cheap silicon chip. We sputtered some niobium titanium nitride, that is the superconductor that we used. Sputtering is essentially, having a block of metal in one place and then bombarding it with lasers and high energy particles to make it a vapor. And then these gaseous particles will now go deposit onto your chip, which is hanging upside down on the top of this, fabrication device. So after we sputtered this superconductor everywhere, we then put resist. Resist is used to make these patterns that you'll see. So after we put the resist, we used the maskless aligner to make certain patterns. So in this example, I've just sort of shown this trapezoid as my pattern that I want to create. And this is created by a 375 nanometer laser shining light onto my resist. And this will sort of weaken the resist, depicted by the color change. And then once you do sort of this exposure bake at 110 degrees of your chip, it really weakens up, which can get rid of all the resist that's not meant to be in the development stage. Once you do that, there's also a stage called reactive ion etching, which essentially you expose your chip to a bunch of oxygen and sulfur, etc. That gets rid of the niobium titanium nitride layer where you don't want it. And then when you wash it off using certain chemicals, you're left with your pattern of the superconductor. So here's sort of the chip I was referring to. We have these circles everywhere, are these indium bumps. And then these long squiggly resonators you see are made of superconducting material. And these are the ones that are used to do the readout of your qubit. All right, awesome. So I think we're on time. I want to go over now sorry to bombard so much information, but I really wanted to give these two big platforms that are currently used for quantum computing to you. And one of them was semiconductor spin qubits. The second one is superconducting transmons. So for this, I'll actually use the blackboard for a bit. So now completely changed physics topics, right? Where we were in semiconducting class, now we're, we finished that class, we're going to go to superconducting class. Here we have a simple circuit with an inductor of inductance L and a capacitor with capacitance C. You can think of sort of the voltage at this top node as phi. And you might say, okay, well, what is the Hamiltonian of this circuit? What is the total energy, so to say? Well, using some equations from electrical class or physics class, we can say it's this, where Q is the charge on the capacitor, phi is the flux through your inductor. And if you do a bunch of substitutions, I will write it in a different way, which can help us see why this is useful for quantum computing purposes. Awesome. So there's a detailed sort of step-by-step math process for all of this documented, and I can share that with you. But essentially, take for granted that this is our total energy, where EC is just some constant. E squared by 2C, C is the capacitance. EL is another constant. Where phi naught is the superconducting magnetic flux constant, essentially just a constant, just like E, the charge on an electron. And N is the reduced charge on this device. So once we take this device to cryogenic temperatures, which is super cold temperatures, and we scale down the size as well, these can start becoming these things called quantum operators. Let's not get into the nitty-gritty quantum mechanics of it, but essentially you can think of how many electrons are in the circuit and what is the flux through the inductor. Now, if you plot, and I will use this back, if you were to plot the energies of this Hamiltonian, the eigenenergies, you would notice that they're quantized because of quantum mechanics, and they're equally spaced. This is a quantum harmonic oscillator, and sort of the difference between these two energy levels is, let's say, some omega 0,1. Now, the way so this is actually a pretty, we didn't take too much time to get to the qubit part, but essentially, the x-axis here is phi, and the y-axis here is energy. So the energy of our circuit depends, the energy of our circuit is discretized in these states, 0, 1, 2, split by omega 0,1 of frequency. So this means if I excite this circuit with, say, light of frequency omega 0,1 with energy h bar omega 0,1, I can create a transition between the 0 state and the 1 state, right? And that's how I can do, I can change the state of our qubit. However, because these energies are equidistant from each other, there's nothing stopping this excitation from going to this 2 state, the 3 state, and so on, right? So you have this co-even state. All the states that are possible in this harmonic oscillator get activated just because of me exposing this little burst of microwave pulse for some time t. And that's not useful for us quantum computing people, because we want to isolate this 0 state and this 1 state and play around with it. So what should we do? This equidistant nature comes from the linearity of our circuit. Because all the elements in our circuit are linear, that is where this omega 0,1 being equal to omega 1,2 is coming in. So what if I replace the inductor with a nonlinear inductor, something that has nonlinear characteristics. Suppose the current through this inductor behaves nonlinearly on one of the parameters. And that is where I get to introduce the Josephson junction. And essentially, physically, what this is it's two layers of superconductors split by a layer of oxide. So here you have aluminum, let's say, well, as your superconductor, and in the middle you have aluminum, some oxide, right, as an insulator. And what this creates is a Josephson junction, and Brian Josephson figured this out a bunch of years ago. And one of his relations is that the current through this device depends sinusoidally on the phase difference of the superconductor at both sides. Essentially, where IC is the supercurrent through that superconductor. Essentially, this nonlinearity, if you substitute back into our Hamiltonian, will get you an energy profile that has some enharmonicity, where this is your 0, this is your 1, and now omega 0, 1 doesn't equal omega 1, 2. And now if I initialize my qubit in the 0 state and apply a pulse with frequency omega 0, 1, I can now cause coherent transitions between the 0 and 1 state, doing single qubit operations. Does that make sense? Yeah, awesome. And the symbol for this device, if that is of interest, I will draw it here. Our circuit becomes like this. Right? Here's our transmon, here's our capacitor, and here's our Josephson junction, here's our capacitor, and here's our transmon. Right? Here's, great, we have this established, we have this in the lab as well, but now I tell you to do the following, right, for a PhD thesis or whatever. I want to tune this frequency. So say this frequency omega 0, 1 is 5 gigahertz. I want to be able to tune this. I want to be able to control this. How would I do that, right? And here's an engineer solution that you can do. You can create a device that looks like this. So this is called a superconducting quantum interference device, or a SQUID, where you have your superconductor at the top and bottom, and these small regions of oxide. And what this creates is that it creates a closed loop through which you can now thread a flux. And depending on the value of this flux, let's call it phi external, I'm able to tune this transition frequency, right? Again, there's obviously math and physics to prove this. I'm just telling you and take it for face value. Here are some, actually, if you look at this plot right here, this picture, this is actually an image of the superconducting chip that the quantum device group in ETH Zurich uses. And you can see these different colors that correspond to different things. And I'll give a brief description of each of them and what they are, and then draw on this plot as well. So let me actually make this a little bit prettier to look at. Let's say, okay, phi external. And then we also have our capacitor, let's say. Great. So here's our qubit. Here's all the yellow stars. on the diagram. This is pretty straightforward. We have our qubit. Let's label it 1. We also have these drive lines. What these drive lines are essentially, little lines that come super close to your qubit. And like I've been drawing this little squiggly line saying, okay, I need to excite the qubit. This transmission line actually does this excitation by sending in some sort of pulse here. Right, so this is drive line. There's also flux lines, which means how do I create this external magnetic field? Well, I will just put some line over here very close to it, and then bring it to some edge of my chip. And then if I send an oscillatory current through this line, that causes a magnetic field, which will thread my SQUID. There are also readout resonators, which, if you saw earlier, could look like this. And this is also something you see here in red. So here's my sort of transmission line going from here to here. And depending on the transmittance of my signal, suppose I send a signal of some amplitude, how much of it is transmitted? That value depends on the state of your qubit because of this interaction, right? So here you have your readout resonator. And finally, this is called the feed line, which actually hosts your readout resonator. There's also Purcell filters that you can use to optimize your circuit, get rid of noise, amplify your signal, et cetera, et cetera. And this is sort of the whole picture behind any superconducting chip today. Any questions on that? If not, in the last 2 minutes, I will go over the sort of quantum ecosystem picture and also talk about QSight. So here's sort of the market picture of a bunch of the players involved currently. You see that there's a big focus on hardware. On the right side, you can see companies like Blue Force that send in the cryo equipment needed to make this happen. You see companies like, where did it go? You see companies like Intel, PsiQuantum, Xanadu. There's also IBM here that are actually creating. IBM, Rigetti, these are the companies that are actually creating these quantum devices. These companies mainly have PhD employees that have done research work in the field, and that's why they're at this sort of scientific position at these companies. You also have software companies, which means, great, I have a quantum computer, but how do I access it? How do I tell it what to do? How do I know what pulse to send for how long, et cetera, et cetera, et cetera? That comes through programs, right? Quantum programming. You can write Python scripts saying, okay, I want to produce this gate, Hadamard, let's say. That will then go into a compiler to sort of take your bigger algorithm into picture and then send instructions to the hardware. So a bunch of these companies are involved. And then finally, on the very left side, you have your users. They kind of, they're there just to make money, and they're trying to use all of these resources to benefit their company. So you can see JP Morgan, Volkswagen. There's also DARPA, Bank of America, so on and so on. There's a bunch of them. And one of the more popular ways, I guess, not one of the more popular ways, one of the ways also how these companies are formed, these hardware companies are formed, are by simply like research groups in universities spinning off into companies and startups. So for example, DIRAC is a company based off of Sydney, Australia, which came out of Professor Andrew Zurac's research group. Right? So that is also one way companies could be fed into this ecosystem. So I won't go over that, and I'll put up some resources that you can go to if you want to learn more about this field in the future. We have a U of T Quantum Computing Club here at U of T. I'm one of the co-presidents, and Michael Silver, if you know him, he's also part of this initiative called QLearn. He teaches quantum algorithm lectures. I teach quantum hardware lectures. 1 hour per week. No commitment, no GPA requirements, whatever. It's just a fun time. You come, we talk about this exact thing that I've talked for the past 60 minutes, but slowly and more methodically. And it's a fun time, right? So here's the QR code if you're interested. Again, we have all of this on Instagram. And finally, QSite. What I'll say about this one is that it's happening in just a couple of weeks. Actually, our hackathon is starting next week, where we have these challenges provided by companies like Classique, IBM, Xanadu, Haiku, etc. So these are industry leaders providing actual problems for you guys, undergraduates, to solve. You can do it in groups of 3 to 4. Registration is open now. Scan your QR code and go to our website. We also have a bunch of panels, talks, networking sessions, food. One of the coolest panels that is happening is the Future of Quantum Computing panel. We have the CEO of Xanadu, Christian Wiedbrook, coming in. We have a quantum venture capital firm coming in. And we also have a career panel on Sunday to get all that grad school, jobs, et cetera, out in the open as well. So if you have questions, come up to me anytime. Those are my information in the bottom left. Take a picture. There's also our Instagrams written. Yeah, thank you so much for listening. And if you have any questions, feel free to reach out.
Is this working? Yep, looks like it.
Okay, I've never taken a quantum mechanics class, but what is a quantum dot?
Quantum dot. I should have explained that further. Quantum dot is not something you learn in quantum mechanics class. It's something I came across in my research. It's essentially the transistor that I showed. So maybe it's actually on this plot as well. No, never mind. So here's a transistor that I showed earlier. Just this region here in which you can isolate your electron, we call that the quantum dot, because it's a dot with 0-dimensional confinement, where we can just place an electron or 2 electrons or 3 electrons and so on.
0-dimensional confinement.
Yes. So 0-dimensional confinement means that it's confined from all sides, such that your state, whatever particle that you have trapped in it, has its wave function in 0-dimensional. It's no, wait, that's not a good way of explaining it. Sorry? Yes, it's stuck in the sense that it cannot move in any of the 3 dimensions. Exactly. So if I just throw a tennis ball in the air, it's in 3D confinement. It can move anywhere in 3 dimensions. If I roll a ball on this table, it's in 2D confinement. If I send electrons through a wire, it's in 1D confinement. And if I, do one more restriction, it's 0D confinement. Cool. Yeah.
Off topic, but it might be a bit off topic, but I want to ask about the Josephson tunneling.
Yeah.
If I remembered correctly, when there's 0 voltage, it can possibly give a direct current. Is there any intuitive explanation for that, or that's just from math?
It is from math, but obviously everything you can create an intuition. And the intuition I could drive is that
from what I remember, the change of the phase, like the rate of change, is proportional to the voltage.
Right.
So integrating can give a constant term.
Yes, but that's math, right? So I don't know if I can give you an intuition for why that that can happen. If you look at the equations, maybe we could come up with some intuition for, okay, well, there has to be a closed loop. Suppose this is a closed loop. The wave function of your electron has to close in on itself, and because it has to close in on itself, you're going to have this particular solution which creates current to some degree.
Oh, and the energy levels are not evenly distributed. Is that just can that be calculated from math, or do you need numerical simulations to get?
No, you can definitely calculate using math. If you plug in that sign of the Josephson relation, current equals critical current times sine of phi back into, or you'll have to actually calculate the Josephson energy, the energy of your Josephson junction, and then you put that energy value into the Hamiltonian, and you solve the Schrodinger equation to get your eigenenergies. Then you'll see that they're nonlinear.
Yeah. Okay. Thank you.
So are there dedicated like programming languages for like quantum computing, or is it just like dedicated compilers?
Sorry, the last words?
Are there dedicated programming languages, or is it just like dedicated compilers for like existing programming languages?
So, you know, you have to have a company that allows you to do this quantum programming, and there's a bunch of companies that do that. IBM and Xanadu come to mind since they're at the top. Both of their quantum programming languages, called Qiskit for IBM and Penny Lane for Xanadu, they both use Python-based scripting. So you don't need to learn syntax and whatever nonsense to start programming quantum computers. If you know Python, you can straight up do, Q dot circuit parentheses 0 blah 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 and start programming that way. Quantum compilers is something that you as a user don't really have to worry at this stage.
Okay, so you went over this, but I don't remember why, or the explanation for why the setup makes it so that the energy levels are equidistant.
Wow. So
Like the first diagram you drew. Yeah.
So the circuit that I drew, it was this. We have a capacitor and an inductor. Both of these are linear devices. What this means is that the relationship of the voltage across this capacitor and the current through this inductor depends linearly on some quantity, right? And that's the two fundamental equations for these devices. Whereas for your transmon qubit, it's this sinusoidal function. So because the behavior of this device works sinusoidally, you get these nonlinear energy levels. Because these devices are linear, and because now you're going to do a bunch of math to find the energies, at the end of the math, you get linearly spaced energies.
Okay, thank you very much. I think that's all the questions. So one final round of applause for Vivek. Thank you very much. And we still have some cookies left, so feel free to grab some of those. Thank you for coming.